Hello, I welcome you all to this another interesting screencast. The problem reads, and the second problem, we already solved the first one. At the instant theta equal to 60 degrees, the boy's center of mass G is momentarily at rest. Determine the speed and the tension in each of the two supporting chords of the swing when theta is equal to 90 degrees. The boy has a weight of 60 pounds. Neglect his size and the mass of the seat and the chords. So momentarily, both problems are coming from the engineering mechanics and dynamics of 14th edition by R.C. Hibbeler. So momentarily, the swing or the boy on the swing is at rest at theta equal to 60 degrees, and then later on it moves to 90, right? It moves to 90 degrees. Okay, somewhere there. Right. So this angle that he covers is 30 degrees, right? Because if this is 60 and then we have this one which is 90, and 90 minus 60 is 30. So this is the one that we want to find. We want to find what happens from 60 degrees to 90 degrees. So let's draw the free body diagram. We have the weight, of course, here. All right, red. Okay, it's okay. And this is going to have components. We are going to have components along this axis. Okay, we'll have components along that axis and this axis. I'll make this one short. Right. We also have the tension in this. We do have the tension. So if I was to show it at the point of sectioning, we are going to have two opposing or two like so in different direction. Remember, right? Newton's third law. Okay, like so. And then I want to call this axis. I'm calling this axis my n-axis, and then this one, okay, it's like this, right? Something like that. It has to be perpendicular. It has to be perpendicular. I think this is perpendicular enough, is it? It can't be more than this. Okay, maybe up to somewhere there. Something like this. Let me rub this. I will draw it once more again. I will draw it. So have something like so. Okay. This component must be collinear. Okay, something like so. Great. So what else do we have? Let's show the angle. So if I was to draw a horizontal line here, okay, then we know that if this is theta here, therefore we expect which one to be theta here. Okay, so we expect this one here to be theta, and if this is theta, this will be 90 minus theta, and this one here will be theta, right? Great. So once we've established that, then we can indicate that angle there is theta. Okay, great. So we said this is W, which is equal to mg. This one here is the n coordinate, this is the t coordinate, and this one becomes W cos theta, and then this one becomes W sine theta, right? So now let's write down the equations of motion. Right, so we are on case number 2. Okay, we already solved the first case, and this is the one we are working on is 13-61. 13-61. Of course, we'll need to find the velocity first for us to find the tension. So let's start with the summation of forces, or the equation of motion along the t-axis. So we'll say summation of forces along the t-axis. This is equal to mat going down, being our positive reference. Our m is just equal to 60 divided by 32.2. Okay, what else? And our w is just equal to 60. So what do we have there? We have w cos theta is equal to mat, and making 80 subject to formula, we need this. It just becomes cos theta divided by m, and this is equal to 60 cos theta. We are writing this in terms of theta because the swing is moving from theta equal to 60 to theta equal to 90. Right, so this is just 60 divided by 32.2. Therefore, our 80 is just going to be equal to 32.2 cos theta. Alright, so let's use this kinematic equation. ADS, remember this, ADS is equal to V dV. This comes from the two equation, V equal to ds dt, A is equal to dV dt, making dt subject to the formula, then we come up with this equation. But when you look at this equation, our A acceleration is in terms of theta, therefore we need to integrate this left side with respect to theta. Right, so we know that given a portion, this portion like this, and an angle here like so, and then this arc distance s, and this is r, we know that s itself is just equal to r theta. Okay, and this can also be written, okay, using infinitesimal small sizes of s and theta as just s is equal to r d theta, right? So this is the concept that we just want to use. Therefore, we'll say our ds is also equal to just r d theta. Okay, is from derivatives. Okay, so if we are to replace this here, if we are to replace this one here, okay, therefore we're going to have a r, and that a there is 80 that we are going to replace. Then we have r d theta is equal to v dv. Okay, so then we integrating. There we have theta 1 to theta 2. Okay, or theta naught to theta. There we have v naught to v. Alright, and we know that our theta naught there is 60 degrees and our theta is 90, and our v naught, this is held momentarily at rest, therefore this is equal to 0, and our v there is just equal to v, or you can think of v final. Okay, so writing this and replacing our 80 in there, we want to replace this one there. Once we do so, then we are going to have the following integrating from 60 degrees to 90 degrees. We have a 32 there, 0.2. Okay, I'll put a 10 there. Then there's a cos theta, then the theta. Then this is just equal to integral from 0 to theta of v dv. Working this just becomes a 32.2, by 10, just becomes 322 sine theta. Evaluating this from 60 degrees to 90 degrees, then this side will just have v squared divided by 2. Okay, our v squared therefore will just be equal to, v squared is just equal to 2, okay, by 322 sine theta from 60 degrees to 90 degrees. Okay, squaring both sides. Okay, squaring both sides. Then we'll have our v is just equal to, once we work out that one, just becomes that's 2 by 322. Okay, times in brackets sine 90 minus sine 60. Sine 90 minus sine 60. Okay, and square root of that, we have a 9.29 feet per second. Alright, so once we found this, then we can move on to the next step, so that we find the tension. So let's write down another equation of motion along the n. So summation of forces along the n, this time around going in this direction being our positive, this is just equal to m a n, where our a n is just v squared divided by rho. Alright, so let's write down what this is. So we have 2t, okay, minus w sine theta, okay, this is equal to m a n, right? Okay, let's make t subject to the formula. This a n is just equal to m v squared divided by rho. So making t subject to the formula, this just becomes t is just equal to 2 goes the other side. You can write this as just 0.5. So we have t is just equal to 0.5, and then there we go. We have m v squared divided by rho, and plus w sine theta. Okay, our theta, okay, our theta is equal to 90 degrees, right? 90 degrees. We're finding the tension of the two supporting cables when theta is equal to 90 degrees, right? So let's plug in everything. We have w, we already know what it is 60, and we have m, which is just 60 divided by 32.2. okay, that's the weight divided by the acceleration due to gravity in feet per second squared. So t is just equal to 0.5. okay, what do we have? We have 60 divided by 32.2. Alright, we have v. I didn't indicate the v there. Let me move this down. Our v, we are just from calculating it, is just 9.29. So we have a 9.29 squared divided by rho. Our rho is equal to 10. So this is 10. Then plus 60 sine 90 degrees. So working out this, our T comes out as 60 divided by 32.2 by 9.29 squared divided by 10 plus that 60 sine 90 is 1 and by 0.5. So we get a 38.04 pounds. Alright, I think this is about it. We can outline the solutions. We have our speed. We do have our speed. We also have the tension at theta equal to 90 degrees. So I hope this particular video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and I'll see you in my next screencast.